Turn on this audio. Can you speak?
I think it works.
It works?
It works,
Okay.
yeah.
You can go.
I think the problem was I clicked.
Yeah. Okay.
Okay, let's get started. Hello everyone, welcome to the seminar in computer architecture. Today we will have two excellent presentations regarding in-storage computing. Hi, Constantina, please introduce your case.
So hello from me too. So I'm Constantina, and I'm going to introduce to you our first presenter for today. His name is Harson Gara. He's a first year master student in electrical engineering, and his research interest lies in the domain of hardware software for design as well as processing in memory. Today he's going to present to us MegIS, which is a work that is actually developed by Safari Group. So the floor is yours.
Thank you. Hello, everyone. Yeah, thank you for the introduction, Dr. Constantina. So today I'll be presenting MegIS, a work from Safari, which was presented at ISCA 2024 this year. And let's get started. So this is what I'm going to go over today. The first thing we usually get through is the executive summary. So MegIS attempts to solve the problem of metagenomics in the way that it finds that there's large I/O overheads, and this leads to degrading performance and increasing energy consumption. The goal of the paper finds is that we need to improve performance and efficiency of metagenomics analysis by reducing the I/O overheads and the energy consumption in a cost-effective manner. The key idea is that you want to enable in-storage cooperative processing, and this is again using hardware software co-design. The key mechanism, like I said, uses hardware software co-design to mask system inefficiencies in different parts and alleviate the overheads. And the 5 techniques it uses are task partitioning and mapping, data computation, flow coordination. The third, storage-aware algorithms. Fourth, lightweight and storage accelerators, and the fifth, specialized data mapping schemes. It finds that through its implementation, it gains significant speed up and energy reduction over two baselines, if you may, Kraken 2 and Metal-line, and then does so while retaining the accuracy of the state-of-the-art accuracy, and it does so with low cost. Going into the background rather quickly, metagenomics is the study of genome sequences in a shared environment. So once you have a sample from a shared environment, you study the content of this sample, and they do so for the purposes of personalized medicine, for outbreak tracing, and for microbial diversity estimations. Specifically, the technique involves the following steps. Once you have a sample from a shared environment, you sequence and base call this particular sample, which gives you a sample read set. From this, you extract k-mers. So k-mers are essentially subsequences of these individual reads. and then compare these k-mers with a database to see if you have hits. If you have hits, you collect the species IDs or tax IDs, which is basically an identifier to say, well, this k-mer belongs to this species. And this particular step is called presence-absence identification because you're identifying a species in the sample. And with this information and the whole input query set, you can estimate the abundance of each species in your sample. That's called abundance estimation. Moving on to some prior art, there are two widely different schemes of presence-absence identification algorithms. The first one is based on random access queries, which is abbreviated as R query throughout this presentation. An example is Kraken2. This particular approach uses a hash table of k-mer to tax ID mappings. So given an input query, input k-mer, you can find the tax ID that it belongs to. The good part about this implementation is that it has good performance, but it results in bad accuracy. On the other hand, you have the streaming access queries, also abbreviated as S-query. An example is Metaline. And this particular approach sorts all the input read queries, and it finds intersecting k-mers with the database. So there's a database that we had gone over earlier. It finds the intersecting k-mers. These intersecting k-mers are again intersected with a sketch database, a database of representative k-mers of these species. This results in good accuracy because you do this intersection step twice, and that's why you have lower performance. Going into the SSD organization, because we want to talk about in-storage processing, let's go over this in a step-by-step manner. So the first is a package. Each package contains multiple dies. Each of these dies contains multiple planes, which contains multiple blocks, which again contains multiple pages. Because there's so much parallelism, you need a smart controller to handle all this parallelism. And this is done by an individual flash controller for each channel. And you have multiple cores that do different tasks. So one of the cores handles the requests from the host. Another core may issue the requests, and then you have various other algorithms running to avoid the side effects of an SSD, things like read disturbances and other background activity like garbage collection. So to do those extra activities, you need metadata, and that metadata is stored in a DRAM on the SSD, a small DRAM. Moving on to MegIS's interests. So we talk about the problem, goal, and idea in this part. We start with the motivation, why really MegIS wants to tackle this particular problem. So the analysis step in the metagenomics analysis, or metagenomics as a whole, is the bottleneck. And the first part to this is performance. So because the analysis step is performed multiple times, you need to optimize the analysis step. And this step is performed multiple times because there is parameter tuning that analyzers do, and they also might change the database because they want to test with different organisms or different species in the potential sample. So the second problem with this is that the step has a significantly low throughput. And moving on to the second part, the energy consumption. This analysis step takes around 63% of the total energy. And this information is taken from, again, prior work by MegIS. So we can conclude that metagenomics analysis is the source of performance and energy bottlenecks in the end-to-end execution, and that we need to alleviate these. To find the specific problem, MegIS performed some experiments for the R query approach and the S query approach. It compares the speed up, the throughput in three cases. The first case, the no IO case, where you have no IO access performed, essentially an infinite host DRAM. And two more realistic systems, the SSD-C and the SSD-P. SSD-C is a cost-effective SSD, essentially lower bandwidth, and SSDP, you have a high amount of bandwidth. We can see that in the no IO case, going from the no IO case to the realistic implementations, we see a lot of loss in the throughput, 40x in the case of SSDC and 4x in the case of SSDP. This means that IO accesses is a bottleneck. You need to alleviate the IO accesses, reduce the number of IO accesses maybe to gain performance. And that's exactly what this is. So the problem as a whole is that metagenomics analysis suffers from IO overheads, and that alleviating this is important because this leads to performance degradation, excessive energy consumption, and lastly, the need for expensive system resources. So SSDP performs better than SSDC. That's because you have higher bandwidth, and generally the solution would be, well, let's just push more bandwidth and then you can get better resources, but better results, but that's not a good solution. You want to use inexpensive resources to solve these problems. Therefore, the goal is we want to improve performance and efficiency by reducing the IO overheads in a cost-effective manner. And the key idea here is that MegIS attempts to perform in-storage processing, but with a catch. It tries to do this cooperatively. It wants to do things inside the storage as well as outside the storage to gain as much performance as possible. And this is, again, powered by hardware-software co-design. So going into the mechanism, unless there are any questions at this point. Great. So in the mechanism, we've already seen this particular image. Let's break this down and see where MegIS makes what changes. So on the preparation of the input queries, this is a picture of, well, you have the host CPU, the host DRAM, and the SSD. The input queries are prepared by the host in the case of MegIS. The first step involves the input query read from the SSD to the host CPU. And here we extract the k-mers. Extraction of k-mers essentially is taking subsequences out of each read. And these k-mers are then allocated to different buckets in the host DRAM. These buckets are sorted based on their range. So for example, the first bucket starts from AAA to CAA and so on. So based on the value of the extracted k-mer, you put them into the specific bucket. And once all the buckets have been populated, you perform sorting on each bucket because S-query approach requires sorting. And you want to perform exclusion. Exclusion means that if a particular k-mer is repeated many times, you don't want to check that k-mer in the database many times. If you do that once, it's enough. And if you have very few k-mers of a particular type, it's quite possible that this was because of a sequencing error. So you can reject them as well. And after the sorting and exclusion is performed, you transfer the data to the SSD to perform the second step, which we'll come to. The reason why this is done is because this allows you to coarsely perform IO transactions. You send a large amount of data in one go instead of repeated transactions. And a second leverage to this is that you can overlap the execution between the host and the SSD, and that reduces the amount of execution time. So the second step is the presence-absence identification, where you try to identify which species are present in the sample. Again, since our input queries are following the S-query approach, you first identify the intersecting k-mers, which I label as step 2A. We retrieve species from the intersecting k-mers, which we call tax ID retrieval. This is step 2B. And MegIS tries to perform this in the SSD because there's a lot of data streaming that occurs. You just read a lot of database entries and the k-mer entries, and you perform intersection. So there's lightweight computation and a lot of data streaming, suitable for near storage processing. This is the whole view of the modifications performed in the SSD. Let's again go over this in a sequential manner. So the first, we have all our queries from the host stored into the SSD's DRAM. in a buffered manner. So you have bi minus 1 and bi, and the database is divided across our SSD channels, and then these SSD channels are queried, and their entries are continuously populated into the k-mer registers in two registers. One is a current k-mer register, and one is the next k-mer register. And the data from the DRAM, the buckets to the k-mer registers is intersected to find if there are intersecting k-mers. If there are any intersecting k-mers, they are stored into the intersection area of the DRAM. So this step allows you to find which k-mers are intersecting. The next step is to retrieve species. Once we know, well, this is a set of the intersecting k-mers, we want to find which species they correspond to. And for this, MegIS uses a sketch database, a modified version of it. I will not go into this at this point, but if someone has questions about it, I've got a backup slide. Essentially, the first thing we do is we read k-mers from the intersection area into the current register and read the sketch database entries one by one into the current and the next registers. Say we have an intersection or a match, the corresponding tax ID is sent to the host. So we've had a intersection essentially. Say the next register contains a different entry. So here we have AATCC, and the previous one was 4 A's and then C. It's clearly different. This allows you to infer that the next k-mer on the in the 4 mers is AATC, which is what is propagated here. This is done using an index generator. This is again a small detail, but I can explain this in more detail if someone has questions about this. The last step is abundance estimation. So given the knowledge of all the species that are present in the sample, you can estimate what is the content of your sample. And this is done, MegIS here supports multiple methods to do this. In literature, there are various ways to do this. For example, you can use statistically, or you can use the read mapping technique here. MegIS supports both of them. And in particular, to support the read mapping step, there is a nuanced implementation. MegIS creates a unified reference index, which combines the reference indices of all the species present in the sample from the information about the species ID present. And you create a unified reference index. And this reference index is used to perform read mapping. This step is performed online because you want to know which species are present in the sample, and only then you create this index. Otherwise, the size of the index would be humongous. Some other details are that the MegIS also modifies the FTL, the flash translation layer. To recap a little bit, flash translation layer contains a lot of metadata for all the background activity that an SSD needs over time. And in particular, one component of this is large, the L2P. Because MegIS doesn't perform any writes after the first step, like in the presence identification step, we're only reading database entries. We don't perform writes, so the L2P can be simpler. You can perform streaming accesses over the database, and that's why you can go for a coarser block level mapping, and that reduces the L2P size and frees up space to store the intersecting k-mers and the k-mers coming from the host. So to summarize the mechanism, MegIS performs specialized task partitioning. So tasks are divided between the host and the SSD. You have data computation flow coordination. Essentially, data is moved between the host and the SSD to perform different computations. You have storage technology-aware algorithmic optimizations, and what this means is that you've tuned modified the way you're performing intersection and tax ID retrieval specific for the SSD, because SSD has you need to stream data from the SSD and not from the DRAM. The next is data mapping. Specifically, we use the MegIS metadata to allow coarser block level mapping. And the last is the lightweight in-storage accelerators in terms of the intersection units to find intersecting k-mers quickly. Moving on to the evaluation. So MegIS performs hardware modeling using Verilog and performs synthesis and PNR. The SSD, NAND, and DRAM are modeled using two simulators, MQSIM and Ramulator. And the software components, in particular, the step one, where we create the input k-mers, they are evaluated using a real machine, an AMD CPU. The baselines that the work compares with are Kraken 2, which is a performance optimized software. It's referred to as POPT in this presentation. Accuracy optimized software, Metaline, is referred to as AOPT. And a PIM accelerator to compare its performance against PIM. And the accelerator used is Sieve. The two MegIS configurations evaluated here are the SSD-C and the SSD-P. And as discussed before, SSD-C is MegIS's implementation in a cost-effective SSD, and SSD-P is MegIS's implementation in a performance-optimized SSD. The datasets used for the evaluation are the CAMI benchmark, and you have three datasets: CAMI L, M, and H. These are in the order of increasing diversity. So you have more number of species in H than say M. And these are the results. So in this particular experiment, MegIS's entire implementation, labeled as MS, is compared against POPT and AOPT. And generally speaking, there is a significant improvement in the speed up. And looking at the averages, we see that over POPT, for both the SSD-C and SSD-P, there is 5 times to 4 times speed up. And over the AOPT implementation, because the AOPT implementation is not fast per se, you have a higher speed up. Therefore, MegIS significantly outperforms its two baselines on both of its implementations. MegIS's different features provide different amounts of benefits. So we've gone over many features of MegIS in terms of we want to do computation in storage, we want to use in-storage accelerators, we want to do overlapping, but which feature really strikes out the best? And if you look at the 4 different implementation, X, MS, MS, NOL, MSCC, and MS. So the first one, XMS, is performing everything that Metagenomics MegIS does, but outside the SSD. So no storage aware optimizations. That's the first one. The second one is MS NOL, MS no overlap. So essentially you do perform computation in the SSD, but you don't overlap the host and the SSD. We see a massive difference and a massive speed up gain by doing computation in the SSD, which shows the benefit of in-storage processing as well. Yeah, so the major source of speed up is in-storage processing. Evaluating MegIS over the PIM baseline, again, there is performance improvement, speed up. And this shows that MegIS systematically tackles I/O overheads. A PIM device would still need to access the SSD. You still make I/O transactions. And that is what's putting down the performance of the PIM. Because MegIS wants to be cost effective, evaluating its cost effectiveness is important. MS_C is MegIS's implementation in a cost effective DRAM. And this implementation outperforms the baselines on a performance optimized SSD. So the performance optimized SSD is, well, you have higher bandwidth, and the MegIS's cost effective SSD is cheaper because you have a cost effective SSD. And showing that there is performance improvement over an expensive baseline shows that, well, it's a cheaper solution. And it also demonstrates performance improvement over abundant in its abundant estimation step. And we look at MegIS's implementation over POPT. There is 5 times and 3.7 times, and over AOPT, again, we have significant improvement. So therefore, abundance estimation also is covered. It performs speed up over. It shows speed up over abundance estimation. For the area and power overheads, we see that it consumes very little area in the SSD and requires almost nothing in terms of the power requirement. It's 7.658 milliwatts. So it has minimal area and power overheads as well. And it shows significant reductions in energy, as much as one whole order of improvement over P-opt and A-opt. Over C, it's a 2x improvement in the energy consumption. So therefore, MegIS is the first end-to-end in-storage processing system for metagenomics analysis. And it does so using task partitioning, algorithmic optimizations, and using accelerators. And this results in a significant speed up. There should be a gap between in and significant. A significant speed up and energy reduction over Kraken 2 and Metal Line. And it does so while ensuring state-of-the-art accuracy and cost. Before moving on to the strengths, if someone has questions about this, mechanism and evaluation, because I understand it was quite dense. Okay. So moving on to the strengths. So MegIS, again, because it's the first in-storage processing solution for metagenomics analysis, clearly this has to be the biggest strength of it. It does the alleviation of I/O overheads beautifully, and it improves the performance and efficiency. MegIS also realizes that doing everything inside the storage is not a good idea. It's cognizant in the fact that if you do everything in the storage, some parts of your workload are going to suffer. So you want to do this mindfully. You want to do things in the host for what it makes sense to do it in the host, and for what makes sense in the SSD, you do that in the SSD. The next is MegIS makes non-invasive changes to the SSD, which means that you can still use the SSD for regular operations without any problems. And that means that you can still do MegIS. The stuff that you add for MegIS doesn't give a problem to the regular operation. MegIS also demonstrates foresight, and this would need some explaining. So I've showed this figure before about how the input queries are allocated to various buckets. But what happens when the input queries exceed the host DRAM? And MegIS says that, MegIS says that, well, if it exceeds the buckets, you have a separate buffer where you can store all the unmapped queries, and these unmapped queries are stored into the SSD. So you still don't have a problem with the host being completely used up. It makes sure that there is a solution for that as well. And as expected from any work of this order, well, you have a rigorous evaluation of the design. But there are many sensitivity studies which are in the backup slides. If someone's interested, I can go over them. And there's a very detailed background about the SSD's organization and metagenomics analysis. Moving on to the weaknesses. So one weakness is that when MegIS is being run, because you have modified the FTL, you've removed the L2P mapping for regular workloads, the finer grained mapping, and you've replaced it with the coarser mapping. Now you can't really run the other workloads. Essentially, your host may idle while the SSD is performing some tasks, some MegIS tasks, and there is inefficiency of usage of your resources that you've deployed. The second was that, well, this was a personal thing. I'm not sure if this is going to be relevant for everybody else, but for me, the writing was quite hard to follow because the description of the mechanism required me to move between steps multiple times. Possibly because there is so much interplay between these sections. There was also some lack of clarity about how the unsorted and unexcluded read queries are handled. So I mentioned the strengths that the queries that go beyond these buckets are directly written to the SSD, but the sorting and exclusion steps are performed after all the input queries are mapped to the buckets. So the ones that have been already written to the SSD are not sorted and not excluded. There is an experiment that describes what happens when the host DRAM is scaled in size, but it doesn't really demonstrate if those cases include the unsorted or unexcluded k-mers. The next is, this was a nitpick. I think MegIS uses a 2-bit encoding of the ADCGs, but it's baselines, they don't use a 2-bit encoding. So for 4 characters, ADCGs 2 bits are enough, which is a great implementation. But the baselines do not do that. The baselines, I believe, use 8 bits to represent ADCGs. But I recognize that our work is not expected to modify its baselines, but it would be nice to see the actual improvement that in-storage processing brings, because we have a lot of data movement happening, and if your data movement is scaled by say 4 times, do we still see the same performance benefits or not? And this is quite relevant because other workloads might benefit from in-storage processing. So you want to see if in-storage processing is something really useful for other workloads or not, and this can be an inspiration work. It would have been nice to see that maybe this is a small result. The work does not provide a breakdown of the SSD's LPDDR usage. So the SSD's LPDDR or the DDR is stores the L2P and other metadata for background tasks. Because our L2P is quite small now, we have space for the intersection k-mers and the input queries. But how much space do we have left after this? Because this can enable further optimizations or data or remapping of our data in the entire SSD to gain more performance and energy efficiency. And the last step, the last one is in the tax ID retrieval step, we are using only 3 channels, or it appears to me that we're using only 3 channels. Because let's say we have a sketch database of 5 mers, 4 mers, and 3 mers. We would end up using only 3 channels, and SSDs are usually provisioned with 8 to 16 channels. And this would become a problem if you have a large intersecting k-mer set, which would mean that you have to perform this many times. I mean, you don't use the entire resource that is available to you. It would have been nicer to do that. Those are all the strengths and weaknesses. If there are any questions here. Okay.
There's a question on Zoom. Is the sorting and excluding step done on the SSD controller's DRAM or before you move to the SSD?
Okay, good question. It's performed before we move to the SSD. So in the first step, all the input queries are read from the SSD to the host. K-mers are extracted and put into various buckets. After all the k-mers have been put into the buckets, one by one, we go over each bucket, perform sorting and exclusion, and dispatch the bucket to the SSD. So yes, it's performed on those. Yeah, please.
So, do you know why the baselines use 8 bits? Do they store any additional information? Or?
I believe it was, no, not for extra information. I believe it was just a choice. I think of recent people have chosen to do 2 bits. The baselines are in 2020s and 2021s. And this was
just like the closest choice, right? You have 4 different things and you use 2 bits.
Yeah, I'm not sure why.
Thanks.
There's 2 questions here.
Yeah, so I sort of have a follow-up to the Zoom question, and that's the question is why. So you also mentioned in the strengths that it's good to separate different parts, like parts where the SS in storage processing is good. Do that in storage, and then separate the rest of the CPU. Do you have any insight on why this bucketing and splitting into k-mers performs better on CPU? Because I could imagine that we could eliminate more data movement.
Right. I think I missed that point. Thanks for the question. So you would want to do that on the host because after k-mer extraction, sorting, and exclusion, naturally perform a lot of writes to the DRAM. If you were to imagine a world where you do this in the SSD, you would want to perform a lot of writes to the SSD. And the SSDs have an endurance problem. The SSD NAND has an endurance problem, so you don't really want to do that. You don't want to do a lot of writes to the SSD. That is one concern. The other point is that you have a larger host DRAM, and because you have a second compute unit in the host, it could be possible to overlap the execution of the first step with the second step. So it's a three point.
So in the weaknesses, you said that other workloads cannot run while this is being run. Could you maybe elaborate on that, or like what other workloads are especially affected?
Right. So when you want to run a workload and that workload accesses the SSD, you need the L2P mapping in the metadata to translate the logical address to the SSD's physical address. MegIS removes this L2P and replaces it with a smaller L2P specific for its implementation. Now, in the absence of this L2P, your workload on the host cannot really get data from the SSD. So no other workload can run apart from metagenomics workload. And if the host was not doing anything specific for metagenomics, MegIS, then it would idle. Well, it can't. Does that answer the question?
Yeah, I also have a question. So one of the sources of benefits in MegIS is that we benefit from internal parallelism. Like we have 16 channels internally, and that provides higher bandwidth compared to the external bandwidth of SSD. So I really couldn't understand the last point you mentioned, the weakness, that MegIS is only utilizing 3 channels or 4 channels.
Yes, this was for the tax ID retrieval step. And in the sketch database, my understanding was that the case they've considered is you have a sketch database with 5 mers, 4 mers, and 3 mers. And from the description, it looked like one of the k-mers, say 5 mer, is the data is coming only from one channel. The 4 mer is coming from this another channel, and 3 mer from another channel, and that's it. It didn't appear to me that all channels were being used simultaneously. Or at least maybe that was an interpretation.
Yeah, I think we can discuss offline. This seems, I can see some confusion here.
Sure.
Because, yeah, actually, one of the main reasons that if you show the results for the X MegIS.
X MegIS, okay.
Yeah, X MegIS is actually doing MegIS outside the storage, essentially, right? And MegIS is doing everything inside the storage. I mean, like
the whole.
I mean, combining the host execution. So one of the reasons that MegIS actually outperforms X and MegIS is that it benefits from the internal parallelism, which is, if we consider 16 channels, we have like twice the bandwidth of the external. So external bandwidth is around, let's say, 8 gigabytes per second. Okay. And internally, you have like 16, 17 gigabytes per second. So MegIS is actually benefiting and utilizing all the channels. There might be some confusion that we can discuss.
Sure.
Yeah.
No problem. What are any other questions? Sorry. Okay. I have some discussion points. I think we have 3 minutes, so I can go over whatever we have. So the first one was, what other applications do we think can benefit from ISP? If there are any answers. The clue here is that you want a workload that has a large operating set, because if, say, for example, it doesn't fit in the host, that's the queue, and you want to perform lightweight computations. That's what would be amenable for ISP. Answers?
Maybe nearest neighbor search in the database.
Yeah.
Quite sure.
Yeah, so that's a lot of them.
So maybe a follow-up question. What does nearest neighbor search has that can make it storage processing friendly? In your opinion?
So I thought of that workload because there's no writing involved. There's inherent parallelism because we want to compare, say, one vector to many vectors. And then also the computation is lightweight. It's like I guess a dot product.
So I will that. Oh, do you want? Okay. So the answers that I come up with is machine learning, in particular recommendation systems, because they have a large, weights. Essentially, traditional genomics can also have an impact from such a technique, and well, database management. And some, actually, in fact, some works have. Yes, please.
You can finish it, but I can also ask afterwards.
No, it's good. Hello.
And can you elaborate on machine learning?
Yes. Well, so one of the works, RecSSD, performs recommendation system analysis. I mean, implements recommendation algorithms in the SSD because I believe the SLS operation is memory intensive, and that performing in the SSD can give you benefit. The only catch here is I believe that some current machine learning operations perform a lot of GEMV and GEM, and that they may not really be lightweight per se. That's what I think about it.
Yes, exactly. That's actually what I wanted to elaborate on. And that usually, machine learning tasks are also computationally quite intensive. You get SSDs, quite a big challenge. So I was a bit surprised seeing machine learning as a first point.
Yeah, but I would assume that if the workloads are matrix vector, like extremely wide vectors, it could still work. Like if it's matrix multiplication, then definitely won't work.
I mean, yeah, but I mean, one of the reasons to accelerate this, we have, for example, GPUs, right? So like if you do it on a very large scale. I guess that.
But in my opinion, okay, this is in GPUs you also perform a lot of batching because you want to leverage matrix operations using tensor code. That's like because I think you batch matrix vector operations to convert it into a matrix operation.
I think it's fine. Thank you very much. I think we can talk later.
Of course. Yes, please.
I had a question. The third one you had on the inside of this database, and actually there was one that I wanted to say first, but then I thought about the second and realized that, for example, in workloads like map reviews, isn't the computation done on the data very diverse? Do you think that it's a problem that you can't have a fixed work computation that you do in storage, but that it's quite diverse? Is that a problem?
Yeah, so if you want to implement something in the storage, you want to do something lightweight, like in specific operations. Maybe not the entirety of it can be offloaded if some particular workload within database management systems requires some specific operation many times, then it would be a good thing.
I see that. That makes sense.
Okay. Do we have some more time or okay?
Maybe I ask.
Yes, please.
So what do you? So how do you compare ISP, like image processing, with processing in memory?
Yeah, I've got a slide for that.
Okay.
Yeah. So well, these were the other two works I've found online. This was about data analytics, and this was about database management. So if someone's interested, maybe we can have a look. I haven't had a deeper look about them yet. But
Are there some takeaway messages about, what should be the characteristics of the applications that you can think, make them storage friendly, like ISP friendly?
I think I had a slide, but I moved that. But I can answer the question. So, in my opinion, workloads that are ISP friendly have to have a large operating set. in the case that they don't fit in the host DRAM. The second point is you want to perform lightweight computations because you don't want to use a lot of real estate on the SSD, and ones that don't perform a lot of writes. If you don't perform a lot of writes, it's good for the NAND. That's what I think, in my understanding in the reading of the paper. Do you have anything else to add to that?
Yeah, I think these are good.
Okay.
To start.
So yeah,
Maybe other folks can also provide some thoughts.
sure. So do you want me to put this question to the audience and give it as an answer, because this was a question posed by you? So this was a question posed by you. Do you want me to just answer this or pose it to the audience as well? So the last question, are PIM and storage processing similar? If someone wants to have a shot at this. Because this is an abstract question.
And the PIM things we see, they are still specialized for certain hardware, but for certain applications, but they don't require as lightweight of computation as I think you proposed that in-store computation should use. So I think there's been either for machine learning applications, right, having like a lot of compute for matrix multiplication more, or the UpMem one, which is completely general compute, on the storage. So I think people are more willing to give up more real estate for computation in the DRAM, but then it's smaller than the storage, so maybe it's useful for things that actually fit in the DRAM.
I think I agree with you. So yeah, my opinion is that, well, they're not entirely similar, but there's also some commonalities. The only commonality I think is that both want to compute near the data, but there are differences. So PIM is not useful over ISP when you can have page swaps. Essentially, this is what I was referring to about wanting to do ISP when your operating set is larger than the host DRAM. The second is that, well, if you have a lot of writes, then ISP may not really be that useful. If you want to do some reduction kind of operations, ISP can be a good candidate. But that also has its caveats because you need to manage the parallelism, you need to be worried about the LTP, and quite a lot of things that you need to consider. That's my answer to the question. If there's something else.
No, I'm kind of agree with what you said. I can maybe add something more that essentially data-centric computing means that doing computation where it makes sense, where data resides. If your data is meant to be inside the storage, you want to keep it inside the storage, maybe it's better to cross it also, complete inside the storage. But if you want to have your data inside the main memory, so you can also you can consider P. But essentially all these processing memory, that can happen in different memory hierarchy levels. The storage is also, so I don't really see difference between ISP and PIM. Both of them are the same thing. We just come up with different names, I would say. But we can consider, so the in storage processing that you're talking about here is like near flash memory computing, let's say. And PIM also can be near like DRAM. It can be also near SRAM, like near cache. So then
I think it's just nomenclature.
Another thing I'd like to also add is that in storage processing, operation is usually slow because of the flash access time. But sometimes we can benefit a lot from the parallelism that we have there. So then also is a trade-off between latency sensitive applications and bandwidth sensitive. So PIM might be faster, like processing inside the memory, the main memory might be faster compared to flash accesses.
Yeah. I agree with you on the memory because it's processing in memory, not processing in host memory. So I had another point. I think we're running short on time. I'll just finish this one. So is cooperative execution enough? Should you also worry about the participating compute units being idle? So let's say in the case of MegIS, you have the host CPU and the SSD's controllers and the SSD's accelerators. You want to make sure that all of them are utilized to its most to do meaningful work. So my opinion here is that we want to ensure maximum utilization and that you could do this by pipelining the workload. In the case of MegIS, maybe we partition parts of our input read query set instead of fully mapping the input read query set to the buckets and then performing the execution. Instead, we could make smaller chunks, smaller buckets. It could mean more execution, but there could be a trade-off there where more execution can still result in speed up due to pipelining. So that's one point. The second point is where you want to permit other workloads to be executed. This is a constraint of the SSD's DRAM capacity. If the SSD's DRAM capacity can be scaled, then we can retain the prior mapping as well. But that's what I had. And yeah, this is relevant for MegIS as well. Yeah, just said that. And LLMs, but maybe not in storage. I will not be able to do that because of the computation that you want to do in LLMs. This commentary about the LLMs is more about cooperative execution in general.
For LLM, actually, there is a microcontroller that they are doing the flash. They are doing the LLM instead flash memory.
Nice.
But that's with adding logics to the flash in a chiplet design. So I also actually have a question. So I agree with the permit execution of other workloads. That's actually a fair point. But I'm not sure about the pipelining the execution of the work because MegIS has already also implemented kind of pipelining. So while the host is working, ISP is also working. So it's not like we are done with the host and then we go to ISP. You know, we keep both running at the same time.
Okay, what I was referring to was something about this, the bottom here. So after this point, the host doesn't do anything.
Oh yeah, that's true.
Yeah, so I was maybe talking about if this is the whole data set, we take half of the data set, do this bit, and then issue the SSD execution. That is what I was referring to. Yeah.
But we can continue for other input data set, right?
Yeah, that's also a good idea.
Is that possible?
Just,
I mean, separating the two data sets, I would feel like that would be.
oh, sorry, they're not data sets, the input read queries.
Yeah, but the input read queries, like if you separate them, let's say into n chunks, then at some point you need to combine the information again. And I feel like that combining the information is not that trivial.
So the step that's performed in the SSD is just presence absence identification. We're identifying which species are present in the sample. We would just perform some redundant computation. Essentially, it's possible that we find the same species ID in the next chunk again, but that's about it. It would not be difficult to combine, in my opinion. If you, I mean, I don't know if that makes sense, but I can do that.
So my concern was that if you treat these, let's say you treat the input read queries into, I mean, in a pipeline manner that you see, then later when you do the bucketing, you cannot have in one bucket the reads from the separated input sets.
Okay, that's not what I was doing first. So let's say you have one chunk of the input read queries. You perform the bucketing, the sorting and the exclusion, and you issue them. Once you've extinguished all the k-mers in the buckets into the SSD to perform the execution, you bring the new queries, the second chunk. Okay, that's fine. Thank you. But we can discuss further if that doesn't make sense. I mean, I think we're short on time, so I'll wrap this up. I will skip over these slides because they're minute. But that's all I had. If there are any other questions, I can answer well. Otherwise, we can hand it over to the next candidate. Thank you so much.
This is one that's working. Lenny, do you want to have a break? Do you want to have a break? Do you want to have a break? No break.
Well, a bit late, so I think maybe directly start the second presentation. Maybe I can introduce you first. So our second presenter is Zhihao Li. He's a second year bachelor student for computer science at ETH Zurich. He's interested in to enhance the efficiency of power systems. Today he will present a smart unit. This work is to accelerate large language model training using near storage processing in a real system. It's not good. Yeah.
That's fine.
Testing.
Can you speak?
Okay. Okay, please go ahead.
My name is Zhihao. Today I want to introduce a topic about Smart Infinity, which is a system to training a large language model faster in real world by using near storage processing. First of all, is executive summary. And in previous work, we have addressed the problem of the memory consumption limitations in large language model training. But we have the problem of the bandwidth bottlenecks in our storages. So we want to solve this problem to reduce the data traffic between our devices. Our goal is to first reducing the data traffic between storage, and we want to optimize the storage manager system to handle the data transfer better. After that, we want to scale the system. Then we can apply multiple CDS computational storage devices to get a better performance. We found that the most memory consumption and data traffic transfer in our system is about optimizer parameter, optimizer states and gradients. It counts up to 50% of our consumption. Then we designed the Smart Infinity system. It has 3 components. The first is smart updates, and we can update our gradients and optimizer states in our storage by using layer storage processing. And the second is data transfer handler. We can using the concept of concurrency to reuse the buffer or overlap the works.
The third component is gradient compression. Then we can compress our gradients in GPU and transfer this compressed gradients to our storage and decompress it in the storage. It can reduce most of the gradients transfer in our between our GPU and storage. When we have the platform with a computational storage device, we use Samsung Smart SSD here, and the software environment is PyTorch in Ubuntu Linux system. By testing them on GP2 and BERT model, we achieve up to 2 times speed up than the traditional uploading model, and we have reduced 75% of the storage traffic, and the scalability of multiple CSDs is also available. Then I want to talk about the paper summary. First, we will go into the background and motivation, and of that previous work, and then the topic of today, the smart infinity system. Up that is the evaluation, results, and conclusion. This is a large language model nowadays. The most large language models nowadays is using transformer architecture. It has the property of stability without overfitting, which means we can, when we have more parameters, we have better performance without overfitting. So the large language model nowadays is becomes larger and larger. Here's a basic large language model. The left is encoder, which have attention layer, multi-attention layer. After that, feed forward. It can generate the contextual representation, and the decoder, such as GPT nowadays, has more linear layer. After that, the softmax activation for classification, and using this decoder, we can generate the real-world text. There are so much companies doing this nowadays. In infrastructure layer, we have hardware, interfree, and Venturi. So much things, and in application layer, we can generate code, chat. We have chatbot or copywriting with a large language model. The problem in previous is the memory consumption in large language model training. The most consumption is, I have just said this about the gradient and optimized states. It comes up to 50 or 60% about the total parameters. The second is the model parameters in the weight of the neural network. And the third is activations. It's not so much here. The large language model is increasing from this year's. We can see in the picture that the GPT-4 has approximately about 1.8 trillion parameters now. So, but our GPU memory is limited For a single GPU, we have only gigabits or dozens gigabits memory. Although we can combine multiple GPUs memory to achieve a better performance, but the GPU is relatively expensive. So we introduce the storage offloaded training. Then we can train the huge data without so much GPUs. So this is the storage offloaded training. We can see that the storage has much higher memory capacity than GPU. So we can transfer the critical data from GPU to memory to solve the problem of the memory capacity limitations. However, the bandwidth of the storage is very limited. It's much lower than CPU and GPU. So we miss the bandwidth bottlenecks here because the lower bandwidth of our storage memory. In the previous work, it's about the zero infinity is offloaded training system, just like the previous one, and it's infinite offload engine, which means it can connect with multiple storage devices as we want, and it's memory-centric. So the advantage is it has multiple storage layer, GPU, CPU, and NVMe. So we can transfer the data to NVMe and processing to avoid the limitation of the GPU memory. However, this paper didn't consider too much about the bandwidth of the NVMe limitations. So it has not a very good, the best performance, and we need now to develop the system to address the bandwidth bottleneck problem. Then this is a smart infinity. For the smart infinity, I will first to introduce it, and it has the three components: smart updates, data transfer handler, and data comparison and smart comparison. After that, I will dive into the microarchitecture. First is briefly introduction. Our goal is to training the large language model system using their storage model, and we want to store our critical data such as parameters and such as optimizer states and regions into our storage and update and training them in the storage and in the whole system, we have smart updates, data transfer handler, and smart comp, these three components. First of all, I want to introduce smart updates. The smart update is we have stored the gradients and optimizer states in our storage, and we want to update the value just inside of the storage. Now, I want to talk about the whole training system in each iteration. First, we have a GPU and GPU memory. After that, we have host and CPU memory. This is then our computational storage devices with SSD inside. This is our storage. Yeah. Have much more capacity but lower bandwidth. We store our parameters and activations first in our host memory, and the most consumption, the optimized state and gradients in our SSD memory. For GPU, we process in the forward pass and backward pass for the most computational part. In CSD, we have specific FPGA to implement our updates. So this is our smart updates, the updater. The process is so first we connect this GPU, CPU, and CSD with PCIe. Then we can transfer this data between these devices. The parameter after the forward pass, we have the activations. With the parameter and activations, we implement the backward path, and we can get the gradients of this back to our storage devices. With the original optimizer states parameter gradients parameters of last iteration, we can update them to get the updated optimizer states and parameters. So this is basically a iteration in large language model training. And you can see that when we store our optimizer states and gradients in the storage, we have saved a lot of data traffic in our system. And this system has achieved, have reduced the storage traffic by about 75% already. And it has, and this implements very efficiently and save a lot of resources. And after that is our data transfer handler. The data transfer handler is a storage management system to manage the data transfer inside of the inside of our computational storage devices. Yeah, here is the last graph about the computational storage devices with updater, and we add the data transfer handler to handle this transfer from data inside the accelerator memory and the computational devices, yeah, FPGA. The key technique of this data transfer handler is using the concept of concurrency to overlap the data transfer and reduce the buffer using buffer pre-allocation. You can see here is our naive implementation. We must we must first initialize the buffer in yellow one, and then send the data from SSD to FPGA. Then we compute them in the blue part and transfer this computed data back from FPGA to SSD. However, this implementation have relative lower efficiency. Then we use the buffer and swap the overlapping. First of all, we initialize the buffer, and then we send the send the parameters, momentum, and variance from SSD to FPGA separately. After that, we compute them and send it back. When we for this example, when we complete the parameters, which means the green one, when we send the parameters back to SSD for task 1, we can immediately send the parameter of the task 2 from SSD to FPGA again, without waiting for all the task 1 completed. So we can transfer the data from SSD to FPGA and from FPGA to SSD at the same time, and we save the time on the memory during the training. For example, here in original time, we have just trained 3 tasklets, but here in the same time, we can training 4 tasks in pipelining ways. Yeah, and we have a better, higher throughput, and in this way we reduce the latency of the task and reduce the memory overhead. The next is the smart comp. This is gradient compression tools. This is our previous architecture with updater and data transfer handler. But without the gradients, we must compress the gradient to reduce the data traffic caused by the gradient. So after backward pass, we restore our gradients in our host memory now, and we use the compressor for gradients to compress the gradients in our GPU. After that, we have the compressed gradient. Then we can transfer this compressed gradient using less data traffic to our storage devices. Then when we want to update these parameters, we must first decompress the gradients in our storage. So we decompress the gradients using the decompressor in our FGPA, and using the optimized states gradients and parameters after the followed by the decompressor, we can then update it again to get back the optimized states and parameters. Then this is complete iteration for the training again, and the compression of the gradients has significantly reduced the data transfer between GPU and our computational storage devices. Then let's talk about the microarchitecture, just briefly and fast. The bottom of the graph is our updater. It has P0, P1, P2, which can update the target parameter in parallel. in parallel from FGPA to accelerator memory. Yeah, inside of each processing elements, we have these parameters, and we can use some computational methods. XPBY here is a general averaging for operations. And we can update this value and transfer this back to our accelerator memory. For decompressor, we use the top K algorithm here. We compress the gradients from a matrix into just its value and indices. Obviously, we can also use other compression algorithm other than here. Then the compressed gradients is also back to accelerator memory, and the compressed gradient is back to the compressor. The data transfer handler is between our SSD and the accelerator memory, which can transfer the data efficiently using the concurrency methods. Yeah. Then is our methodology and evaluation. Our platform is the most important is our hardware. The computational storage devices is smart SSD with HPCA and SSD. And software is PyTorch CUDA. We implement on the model in GPT-2 and BERT. The baseline we compare to our Smart Infinity is the previous work, Zero Infinity. And then we can see the results of our Smart Infinity model compared to the baseline. Of each subgraph from left to right, the best is our baseline is from previous work. The Zero Infinity, we just implement the offload training, but not so the bandwidth bottlenecks. SU is we just using smart updates. SU plus O is we using smart updates plus the data transfer handler. And SU plus O plus C here is our overall smart infinity system with these three components. SSD number here is our computational storage devices, which processing, which is the near storage processing. We can conclusion from the graph that after we using the whole system, we achieve about up to 2 times speed up over the baseline. And when we increase the number of SSD, the system performance scaled efficiently. Yeah. And this model, when we change the parameters of the model, our system is adapted very well in different models of different sizes of the large language models. Then this is conclusion. So we have solved the problem of the bandwidth bottlenecks in between storage and CPU and GPU. And using these three components, smart updates, data transfer handler, and smart compression, we achieve up to 2 times or about 2 times of the speed up and reduce the data traffic significantly, and also scale the efficiency with multiple storage devices. So do you have questions for the previous slides?
Just want to make sure I understood the mechanism. So when the updates are performed,
Yeah.
the SSD, you don't have to do that.
Okay.
Do we perform all the updates back to the SSD man, or is there some other, like, does it use some other way to write back the data? When you perform the updates in the SSD?
Yeah.
So are these updates written to the SSD every iteration?
Yeah, we update in each iteration in SSD.
So they're written to the SSD and every iteration. The SSD memory.
Yeah, this parameters to update it is stored in our SSD, and it's processing just near the SSD, and gives the data back to SSD. Yeah. Only the parameter is the inter devices. It may transfer outside of the SSD. Yeah. So I must be quick, so we move on. On the strengths and weakness and takeaways to this paper. The strengths, one is this is multi-layer optimization design. It's reducing the data traffic between host and storage communication by using layer storage system. We store most of the data just inside of the CSD and processing them in the CSD. The second layer optimization is the data transfer handler is transfer the data. It manages the data transfer internal in the devices very well, and it's also reducing the transfer of the reagents between different devices by compress it. A second, the strength is this is a modular design with easy integration. It is with a tight touch integration, so we can just using our original PyTouch code to adapt for this model. The plug and play compatibility means that we don't need to change our original network model in software level. So our Python code keeps the same, and we don't need to change it to adapt with the new hardware architecture. The third one is the optimization is customizable in software level, which means we have just mentioned the smart update and smart compression below. For smart compression, we can use other compression algorithm not only the K-top algorithm, and for the updater, we can also change the optimizer add-on or something else as we want. The second strength is has scalability and flexibility. We can use multiple CSDs to connect to our system to get a better performance. And we can also certainly use multiple GPUs to approve the computational power. And we can apply our model in a large-scale distributed system. We can using multiple smart infinity in a training process or using our model or using the system to training in multiple neural network models. The weakness, the first is this smart infinity system in this paper needs specific hardware. For example, we need a smart infinity from Samsung, and when we want to use another computational storage devices, we may change a lot in specific HPCA level and other hardware level. The second weakness is the data transfer handler mechanism is very complex. When we using our when we using the system in different large language model, the performance may be various because the distribution of these values and data is not always the same, and the better concurrency methods to transfer the data may be various. Yeah. The third one is this paper is only introduced application in large language model training. It may also applicable with other deep learning models with more parameters. And the cost of the system and the energy consumption here is not mentioned because the large language model is larger nowadays. So we must count the energy consumption to maintain our cost efficient values. Yeah. And then its takeaways. So the system smart infinity overcoming the bandwidth bottlenecks in systems and reduce the data traffic between different layers, and the near storage process is promising. We can use this technique in various environments and achieve the efficiency and scalability. Third is a real-world application. It can integrate to our nowadays software environments easily. Do you have questions about the analysis part? So let's move on to the discussion. The first question is, could this smart infinity model useful to other neural network models other than LLM? Why or why not? What is the benefit or what is the weakness to apply to other models? Does anyone want to answer?
Hi. Yeah, so I mean, I guess it could be applied to other models, but it would depend on how many parameters they have or how large they are. If we're going to see a benefit from having your storage processing, because for small models or for things that I can think of outside of LLMs, that you can probably fit what you want in DRAM or on the GPU's memory or somewhere that's not storage.
Yeah. Actually, good. That's right. We can also apply to other models. This may benefit to other models with more parameters or larger models, but the efficiency may be vary because for the small models, these devices we just using a single CSD devices, this might be very expensive, and we can't balance the cost effective value here. So this model is managed for use in the very large models. The second is how would vary the compression rates to impact the accuracy or efficiency of the model. And I want to answer.
I would assume it would decrease.
Decrease.
The accuracy would decrease per iteration. You would gain lesser learning, and that would mean that you are training for longer if you compress the gradients further.
Yeah.
That's my guess.
Okay. Okay.
I wanted to ask about like if the compression isn't lossless, I'm assuming that that's what this slide is about, that some information is lost by the compression and decompression. Must be the case. Is it still guaranteed that your model is convergent? And outside of applications like LLMs where the output isn't necessarily correct or incorrect, like for example in a CNN or if you're doing image classification or something like this, I think that the loss of gradient information can really harm backpropagation because you won't necessarily converge to the result that you're hoping for, or you're losing gradient information as backpropagation.
Yep. Right. Your answer is both correct. When we increasing the gradient compression, we reduce the data transfer bottlenecks, so we can transfer the gradients better. But too high compression rates may cause loss of accuracy and even destroys the overall models. So we must choose moderate compression rates. In the experimental in the paper, it's about 1 to 2%. So we must balance the efficiency and the accuracy by choosing the compression parameters. So this is the last question. what do you think this is the main challenge of this system? In the real world, this is an open question. You can still say what you want. But do anyone want to? Oh, okay, so I will give you my insights myself. The first is this may cause a lot of hardware compatibility issues because the design of specific HPCA or are hard, and the cost of this system may also be high by setting it up. Additionally, because the data transport handler is very complex, so for different models, we must change different management system parameters inside of this data transport handler. So this is very hard to maintain or solve the problem and bugs inside of the data transfer handler. It's mainly a very good expert to maintain the system. The last is we must balance the cost effectiveness of this system, which means the safety devices nowadays is not so. It's also very expensive, so we must consider the price of it, and we must ensure it's easy to integrate to our not only the software system but also the hardware system. We can replace our safety devices as we want when the supply chain have problem. So we can respond it immediately. Yeah. So that's all about my presentation. Thank you so much.
I just remember to attend the quiz after this session, and please also remember to give the feedback to the presenters, all the presenters, including the previous presenters, and also provide the feedback to the mentors. That's all, and thanks to attend the session.